Let me try to explain a critical concept in probability theory which involves joint probability density function and conditional distribution. So the importance of slicing through a joint distribution to fix one variable at a specific values, allowing us to examine the conditional distribution of the other variable. So this technique is particularly useful in understanding how the probability distribution of one variable is influenced by the known value of other. This is a bivariate normal distribution as our joint distribution for two variables x1 and x2, and we slice through x1 equals 0, and we visualize the conditional probability distribution of x2, so we use x1 and x2 with a defined mean and covariance that shows some correlation between them. So the joint probability distribution of x1 and x2 shows how the probability density variables like across different values of x1 and x2, and the perks indicates that the most probable values for x1 and x2 occurring together, which is influenced by the correlation as described in the covariance matrix. When we slice the joint distribution by fixing x1 at 0, we obtain the conditional distribution of x2 given x1 is equal to 0. So this plot is effectively a vertical slice through the 3D plot at x1 is equal to 0, which is showing as the line point. So it displays the distribution of x2, which assuming x1 is exactly 0, which highlighting how the probability density of x2 varies under this condition. Let's consider a scenario where we don't know the joint probability distribution, but instead we use Bayes' rule to obtain the posterior probability distribution. So here we use a simple Gaussian normal distribution as our example. Prior is assumed we have a prior belief about the parameter such as the mean of Gaussian distribution. So the prior distribution represents our initial belief about the parameter before we observing any data. So in this example, it is centered around 0 and a standard deviation of 1, which indicating that initially we believe that parameter is likely close to 0. And then we observe some data and calculate the likelihood of this data given different possible values of this parameter. So this is the likelihood function, which represents the probability of observing data given different values of the parameter. So here, the data suggests that the parameter is around 1 with a smaller variance, 0.5, which indicates more certainty about the parameter being close to 1. The formula is the posterior probability of the hypothesis given the data equals the likelihood of the data given the hypothesis times the period probability of the hypothesis before we observing any data, and divided by the total probability of the data under all possible hypotheses, which is our evidence. So the Bayes rule is a fundamental theorem in probability theory and statistics that allows us to update the probability estimate for a hypothesis as additional evidence is acquired. The last one is posterior, which is we use the Bayes rule to update our belief about the parameter after we observing the data. The posterior distribution is the result of applying Bayes rule, which combines the period and the likelihood, which giving us an updated belief about the parameter after we consider the observed data. So the posterior is shifted toward 1, which reflecting the data, but still influenced by the period, which showing that our updated belief takes into account both period information and the new data.